Morning, good evening to all.
Yeah.
Welcome you all to this webinar, which is on the topic of performance-based structural fire engineering. My name is Alok Bhaumik, and I am the chairman, Professional Development and Technical Events Committee of Indian Association of Structural Engineers. This webinar is being organized jointly by IAStructi, School of Planning and Architecture, and Institution of Fire Engineers India. We have presidents of IAStructi, Mr. Manoj Mittal, and president of Institution of Fire Engineers, Mr. Pravendra Rao, here in the panel to grace this occasion, and I thank both of them for their presence. The topic of the day is extremely relevant to the society at large. We have witnessed several catastrophic, fire tragedy in buildings in India. The statistics is not very good. What I understand is every fifth fire-related death in the world is taking place in India. And therefore, for us, the fire safety assumes a huge importance. Structural engineers generally have very little involvement and exposure in building fire safety. Traditionally, the building codes prescribe certain minimum requirements on fire resistance rating for different building elements. And the structural engineers mostly restrict their role to complying with these.
मेरे को तो unmute दिखाई दे रहा.
Can you please mute others when I'm speaking? Vikas, can you please mute others? Yeah. So what I was telling is that the building codes generally have a prescriptive kind of requirement. That is what we structural engineers are familiar with, most of us. However, the role of structural engineers has been changing over the past 2 decades, and the structural fire engineering is emerging as a distinct multidisciplinary subject in many countries. We are seeing use of performance-based fire structural engineering being practiced. Realizing the importance of this subject, IAStructi and the other 2 associations, we thought it prudent to bring this issue in the forefront of our discussion in the fraternity. And that is the background for planning this webinar. We are very fortunate that we have with us an eminent speaker, Professor Luke Bisbee, who will enlighten us by sharing his knowledge and wisdom on the subject. This webinar will be moderated by an eminent personality in the profession, Mr. V.V. Arora, who is the former joint director of NCCBM, that is the National Council for Cement and Building Materials, a notable cement research institute of India. We also have 3 eminent panelists who will share their views and thoughts on the subject with us today after the presentation by Professor Luke. We have Professor Gaurav Srivastav, who is an associate professor of IIT Gandhinagar, working on fire safety. We have with us Dr. Gopal Mishra, who is the former director of Delhi Fire Service. He is the person who has played with fire in his career. We also have with us Mr. Nitin Gupta, Director RCOP Associate, who is a leading architect and is into planning of buildings. After the lecture by our invited speaker, there will be an interactive discussion on the subject where all the panelists will give their views. Now, before I hand over the floor to the moderator, I have the proud privilege to introduce him. He has recently retired from NCCBM, where he was working as joint director and head of Center of Construction Development and Research. He has vast experience in construction, design, research and development, quality assurance, audit and training. His areas of research are concrete technology, durability, service life design of concrete structures, condition assessment and rehabilitation of concrete structures, including the fire damaged structures. He is playing an active role in many code-making bodies. He is a convener, member of various BIAs, IRC, ISO committees, or panels and working groups, related to the design and construction materials. He is chairman of BIS Committee CED 53, convener working group on revision of IAS 456, material section, which includes properties for design for fire. He has published and presented more than 50 research papers in various national and international seminars in journals. Before I hand over the floor to the moderator, it is a delight for me to invite Mr. Pranavendra Kumar Rao, who is the president of Institution of Fire Engineers India, to say a few words on behalf of all the three associations, that is IAS Shakti, School of Planning and Architecture, and the Institution of Fire Engineers India. Just to give a brief about Mr. Rao, he's a fire safety warrior who has done a lot of work in sensitizing public on fire safety and in imparting training on fire, to various organizations and staff. He has over 36 years of experience on the subject. He is the former director of UP Fire Service and Fire Officer, Oil India Limited. He is also President Fire Services Games Association of India. He is awardee of Fire Service Medal for Gallantry, President's Fire Service Medal for Distinguished Services, and Fire Service Medal for Long and Meritorious Services from Honorable President of India. He developed the first firefighting robot and search camera in India. So with this few words, let me hand over to Mr. Rao for giving his welcome and opening remarks. Over to you, sir, Mr. Rao.
Thank you very much, sir. And good afternoon to everybody. And I welcome all the members of Indian Association of Structural Engineers, School of Planning and Architectural, and others. This is a very good occasion when we all, because you must be knowing that fire service or fire engineering is a multidisciplinary trade, where all the mechanical, electrical, civil, electronic, psychology, etc., this is included in the syllabus of the fire engineering. So you are the expert in this field, and we are very happy to meet you all, and we'll discuss our problem, what we face during the firefighting and rescue with you, and we'll accept whatever experience you are having or research. Regarding the performance-based designing, the National Building Code of India, where the fire safety requirements have been given, there is we don't use performance-based. So this will be a new topic for the fire services, and it will take its own time. So I welcome to everybody, and you can start the webinar, sir. Thank you very much, sir.
May I request the moderator to please take over, Mr. Arora?
Okay. Good afternoon to all of you. We all understand that in view of the wide-ranging material changes, the world is gradually moving towards performance-based specification for all types of designs, like design for strength, design for durability, service life, and similarly design for fire. Somehow we have got a lot of research being done in the country on the other aspects, except on fire, on which we have got lesser research. And we look forward to international expertise and literature for doing such designs and for fire resistance, and even for making codes. Today's lecture by Professor Luke Bisbee is a step in improving our knowledge and expertise in the field. Professor Luke Bisbee, PhD, is head of the Research Institute for Infrastructure and Environment and holds a personal chair in fire and structures within the School of Engineering at the University of Edinburgh. He is a fellow of the Institution of Structural Engineers, the Institution of Fire Engineers, the Royal Society of Edinburgh, the Institution of Engineers in Scotland, and the International Institute for FRPs in Construction. He is a chartered structural engineer in the UK and a licensed professional engineer in Ontario, Canada. Luke is a member of the UK Standing Committee on Structural Safety and collaborating reporting on structural safety. He sits on a number of code committees relevant to structural fire engineering of concrete, steel, and timber structures internationally, and he is a co-editor-in-chief of the Fire Safety Journal, the official journal of the International Association of Fire Safety and Science. Over to Professor Luke Ebisby. Please welcome.
Thanks very much. Good afternoon, everyone. Thank you for joining. Let me just try to share my screen. Hopefully this works okay. Can I just check with someone that you can now see just the first slide, the title slide?
Perfect, perfect. Please go ahead.
Perfect, wonderful. Thanks very much. Thank you for the introduction. That's very kind, and thank you as well for the invitation to speak with you today. As was mentioned, I must apologize. I have a bit of a cold, so if my voice gives up at any point, I apologize. I might cough a couple of times. Hopefully it's not COVID. I've been double vaccinated, so I should be okay. The title of the presentation today is Does Performance-Based Structural Fire Engineering Exist? I was very interested in the comments made a moment ago that in fire safety in India, that performance-based fire engineering is not yet widely done, certainly in terms of the Indian codes. And that's something that I didn't know. So that's an interesting piece of information for me. I am aware from having worked with some international consultancies who do structural fire engineering work that there are specific projects in India where performance-based structural fire engineering has been done on some specific buildings. You know, I in the past have done quite a bit of work with the large international multidisciplinary design firm Arup, and I've also a number of colleagues who work with a company called Bureau Happold, both of whom are active in India and have been doing the type of thinking that I'll talk about today. I should also say before I begin that I'm a structural engineer, so my formal training is in structural engineering, and I got into fire safety engineering. I became interested in fire safety engineering really coincidentally as a consequence of the fact that I was doing a PhD. I started a PhD in structural engineering in 1999, and I was interested in strengthening reinforced concrete columns with carbon fiber composite wraps for increased load carrying capacity. So those of you who are interested in structural retrofit will probably know the kind of techniques that I'm talking about. And we became concerned about the fire performance of those systems because they rely on epoxies, and epoxies burn very nicely. And so we started doing some fire resistance tests. In fact, my PhD supervisor, whose name is Venkatesh Kodur, is quite a famous Indian structural engineer in his own right, and now works at Michigan State University in the United States. In any case, I started my PhD in 1999, looking at the fire performance of concrete columns, basically. And then in 2001, something very significant happened, of course, which was the 9/11 attacks in New York City. And at that time, I was one of the very few people in the world who was studying the way that reinforced concrete columns or columns of any kind reacted to fire. And so immediately my research interests were thrust into the limelight, and everything that has happened since, if you like, is basically history. Structural fire engineering became a very important topic in the 10 years after the 9/11 attacks. There was a lot of research done, both within the academic community and within government agencies, and I got involved in quite a lot of that work. And that led me to where I am now in my career as someone who is a structural engineer who works mostly in fire safety. And that's why I think I may well be the only person in the world who is a fellow of the IStructE as well as the Institution of Fire Engineers, which makes me perhaps a slightly unusual person. In any case, I moved to the United Kingdom from Canada in 2008. One of the reasons I moved to the United Kingdom from Canada in 2008 was because in the United Kingdom at that time, performance-based design for fire was probably 5 to 10 years ahead of basically anywhere else in the world, as far as I could tell. So engineers in the United Kingdom at that time who were designing high-rise buildings we're able to use performance-based methodologies. We're really able to use physics and computational modeling and a detailed physical understanding of fire dynamics as well as structural response to fire in order to come up with really interesting and innovative designs for buildings. And I thought that was really exciting. And so I came to the United Kingdom when an opportunity arose to come to the University of Edinburgh, basically to try to dive into performance-based structural fire engineering, if you like. And having been in the United Kingdom now for almost 14 years, I find myself asking the question whether or not the thing that I moved to the United Kingdom for actually exists in reality. So does performance-based structural fire engineering actually exist? And how would I articulate the difference between performance-based structural fire engineering and a prescriptive approach to fire resistance design, which most colleagues in India who are structural engineers will be familiar with, by which I mean simply designing for a given fire resistance period. You know, you have a concrete beam and you need it to have 60 minutes fire resistance, for interest. So that's the topic of my talk today. And the way I'd like to think about it is in the context of a particular building. Now I couldn't find a building in India that I thought would suit my topic very well. So this is a building in Norway, which I really like as an example of a building that we might consider as structural engineers. This is a building just outside Bergen in Norway. It's an 18-story building, and the structural frame and walls and floor slabs of this building are all fabricated out of a building product called cross-laminated timber. So they're solid timber elements, essentially glued together planks of wood to develop massive timber elements. And you can see the large timber structural framework coming out of the top of the building, but all of the floor plates and walls in this building are also solid timber, several hundred millimeters thick, solid timber, laminated. This building is part hotel and part residential with some office and retail space at the bottom. So it's a mixed use building, and it's currently the tallest mass timber building in the world. So it's a very interesting building from a fire safety perspective. And keeping that building in mind as I talk through the next topics, I just want you to think about this particular building and what structural engineers who've designed this building need to think about when they design this building. What are the considerations that they must keep in mind as they're designing a building like this? And so the way I wanted to think about this, and I should say that what I'm going to talk about today is based on a talk that I gave a few months ago for the International Association of Bridge and Structural Engineers, where I was asked to talk about performance-based design. And I thought probably the best building to talk about is the building that I just showed you. That building is called the Mosjarnet Tower in Norway. And then the question was, because building codes are different all around the world, and they treat the questions of adequacy and requirements for design in different ways, I have to pick a jurisdiction to talk about. And one of the jurisdictions in the world that is widely considered to be the front runner when it comes to performance-based design for structural engineering, both for fire safety and for other types of loads like earthquake, most notably, would be the New Zealand code. So the New Zealand codes went down a performance-based route before most other countries, and they're probably 5 to 10 years ahead of other countries in sort of seeing how the evolution of performance-based design through structural engineering actually manifests itself. And so I thought, okay, well, let's take a look at the New Zealand regulations, and let's ask the question, what would the New Zealand regulations, which are the global frontrunners in this area, what would they say about that 18-story cross-laminated timber building in Norway, the Mosjarnet Tower, in terms of how structural engineers would need to think about it in terms of its fire safety? And I basically just like to walk you through that rationale, because I think what drops out of it are some very important questions about what it is that we're trying to achieve for structures in fire, which is the fundamental basis of why we're doing this in the first place, of course. So before I do that, I just want to say that my personal take, I mean, some people in the world believe very strongly that prescriptive design is the best way to design things and is the safest way to design things. And some people think that performance-based design is the way of the future. And I think different people have different reasons for believing different things. And I think it's important that I say at the outset that my personal view is that I am a strong proponent of performance-based design. So I believe that performance-based design, when delivered adequately, is the best way to be designing buildings. And so what that means is that I spend a lot of my time defending the functional basis of building regulations. So defending the idea that building regulations should not tell people how they have to design things with specific rules. They should tell people what buildings need to achieve, and they should allow people to achieve those things through their designs by whatever means they like. The challenge with that approach is, of course, that everybody within the process of designing and approving and constructing and managing a building needs to have the appropriate level of competence in order to make sure that that work is being done, ethically and at a high quality to a professional standard. And I think one of the problems that we've seen in the United Kingdom over the past few years, certainly since the Grenfell Tower fire happened in London with tragic loss of life, is that when we've actually started to look at the construction industry with a magnifying glass, what we found is that there isn't a lot of competence around issues of fire safety within the construction industry. And the problem is that if you don't have competence, then you can't have a performance-based building regulatory system, because a performance-based or a functionally based building regulation system relies fundamentally on the idea that everybody within the process of designing and approving buildings is competent. And that's required me to have to do a lot of soul searching about what it is we're actually doing when we say that we're doing performance-based design. So I want to talk, in this presentation, I want to talk about really about building regulations and what building regulations tell us about performance-based design when it comes to structures for fire. And I'm going to take, as I mentioned, the New Zealand context as the context within which I want to do this. So the simple question that I'm asking really is, if I'm designing a structure, any structure, to withstand the effects of a fire, or any other loading case for that matter, but I'm going to speak specifically about fire, what level of performance, in quotes, is considered adequate, in quotes? So this question of adequacy is fundamental to performance-based design. If you're going to design something and you want to show that it adequately meets the requirements of a functional objective in a performance-based building regulation, you have to decide what you mean by adequate, which means you have to decide what would be inadequate. And when it comes to the performance of structures in fire, that's actually quite a challenging thing to do. So if we take the New Zealand codes as an example, the New Zealand building code has 3 levels of structure in it. So you can see, I've just copied this from the building code. It basically says the building code has an objective, which talks about the social objectives from the Building Act, and that is legislation. So that is part of the law in New Zealand enacted by Parliament. And then you have functional requirements, functions the building must perform in order to meet the societal objectives. And those are also written in law. So that's legislated by Parliament. And then you have a number of performance standards that underpin the functional requirements and allow you to achieve those things. And those are given in guidance. So that's not in the law, but that is in guidance that sits beneath the law. So if you think about the structure of the New Zealand building codes, and the British codes, for instance, are very similar. The Canadian codes are much the same as well. You have the Building Act, which is an act of law from the New Zealand Parliament. The building code sits beneath that, which is also law. And then underneath the building code, excuse me, you have a number of different methods by which you can meet the functional requirements that are given in the building code. And I'm going to talk about those various methods as I go through this talk. So what do structural engineers who are designing buildings in New Zealand actually have to do when they're designing buildings to resist the effects of fire? And again, keep in mind that 18-story mass timber residential hotel building in Norway that I mentioned a few minutes ago. So if you go to the New Zealand codes and you actually look at the law, what the law says in the building regulations in New Zealand with respect to structural stability is that structural systems in buildings must be constructed so as to maintain structural stability during fire. There is a question of what we mean by structural stability, of course, so that there is a low probability of injury or illness to occupants, a low probability of injury or illness to the fire service personnel during rescue and firefighting operations. So it's not enough that you just get everybody out of the building. You have to make sure that the building remains stable during fire to the extent that there might be fire and rescue personnel operating within the building. And for an 18-story building, that could be a very long period of time. And then finally, a low probability of direct or consequential damage to adjacent units or property. So you have to make sure that your building doesn't fall down either on the occupants or on fire and rescue personnel. And you have to make sure that your building doesn't damage your neighbor's building. And that has to be done so that there is a low probability of those things happening. But of course, the law doesn't say what they mean by low probability. That is left up to the judgment of those involved in the design process. And it's really important to recognize that. So the performance metrics that are stated, that underpin those requirements are stated here, that structural systems in buildings that are necessary for the structural stability in fire, so the structural frame of the building, must be designed and constructed so that it remains stable during fire and after fire when required to protect other property. And in doing that, you have to take into account the severity of the fire that you might get. So you have to take into account the fire dynamics that are likely in your structure, the presence of any automatic fire suppression systems like sprinkler systems, other active systems, and you also have to consider the chances that those active systems, including sprinklers, might fail and that might impact on structural stability. It also says that structural systems in buildings that are necessary to provide firefighters with safe access must be designed and constructed so that they remain stable both during and after the fire, which implies that structures must be designed to resist what we call burnout in fire safety engineering. So the burning of all the fuel without suppression or intervention, such that the fuel is gone, the fire goes out, and the structure is still standing. There are also, however, legislated requirements specifically for the structure. So this is some of the legislative requirements for the structure. So buildings, building elements, and site work shall withstand the combinations of loads that they are likely to experience during construction or alteration and throughout their lives. And in order to achieve that, what the structural engineers are required to do is to make sure that the buildings have, again, a low probability of a number of bad behaviors, so rupturing, becoming unstable, losing equilibrium, or collapsing throughout their lives. The New Zealand codes are very interesting in the second paragraph here, in that they say that there has to be a low probability of loss of amenity as well as loss of stability. So you can't have your structure become unusable as a consequence of being impacted by one of a number of load cases. That's very unusual, incidentally. I've not seen that in other building codes around the world. I think that in the New Zealand context, that is probably because of the high seismic zone that New Zealand exists within. And there have been past events where there have been earthquakes. For instance, the 2010-2011 Christchurch earthquake in New Zealand that caused a great deal of damage to buildings, but did not result in an immense loss of life. And there was a real public outcry after that earthquake that all of the buildings in Christchurch had been so badly damaged that the structural engineering community was considered not to have done its job properly and not to have prevented that damage from occurring. The structural engineering community turned around and said, well, actually, our design codes exist in order to prevent loss of life and injury. Property protection was not something that we were all that interested in. And so I think they added this loss of amenity because of the public outcry after events like the Christchurch earthquake. Anyway, that's an interesting additional requirement in the New Zealand code that needs to be thought about. But what it's important to recognize is that in the structural engineering section of the New Zealand building regulations, they say that account has to be taken of all physical conditions likely to affect the stability of buildings. And that includes fire. So fire is not considered a separate load case. Fire is considered one of the load cases that structural engineers need to explicitly account for when they are making sure that buildings neither lose stability nor experience loss of amenity throughout their lives. So that's what the New Zealand codes, that's what the law in New Zealand expects structural engineers to actually deliver. And the question is, how do the New Zealand codes then tell structural engineers that they should deliver that? And in the New Zealand context, there are 3 routes. And again, they're highlighted in this sort of pyramid structure that outlines the building codes in New Zealand. The first route on the far right-hand side of this triangle, you can see it says acceptable solutions. Well, actually, on the right-hand side, you can see there's at the very bottom, it says you can either follow a deemed to comply route, or on the left-hand side, you have an alternative solution route. A deemed to comply route essentially means if you do this, then legally you will be considered to have met the requirements of the building regulations. And under the deemed to comply route, you have 2 options. You can either do an acceptable solution, and that would be equivalent to probably what happens in India if you only use a prescriptive design at the moment, which is basically if you follow these rules, then it is presumed that your structure will be fine and that you will have met your legal requirements under the Building Act or the relevant legislation. And I'll show you what the acceptable solutions look like in the New Zealand context in a minute. You then also have what's called verification methods. Verification methods are essentially a halfway house, if you like, between acceptable solutions and the third route, which they call alternative solutions in New Zealand. And alternative solutions is really the full performance-based engineering route. But I'll talk about all 3 of these now in sequence, just to give you a sense of where you might fit in if you're a structural engineer in particular working in the Indian context. In most jurisdictions in the world, the acceptable solutions route, or the equivalent of the acceptable solutions route, maybe the prescriptive route it might be called, what the structural engineer does is that they're told, okay, if let's take the 18-story timber building in Norway that I mentioned. That building is an 18-story timber building. Let's imagine that it's a residential building. And then what you would do is you would go to the fire safety codes and you would find out what fire resistance period is required for an 18-story residential building. And you would go to a table like this one. This one's from the New Zealand code. And in this table here, I think the risk group that would apply to the 18-story timber building, I think, is the SM group in this table. So you can see that if you have that building and you don't have fire sprinklers in it, you need to provide 60 minutes of fire resistance. Interestingly, in the New Zealand code, simply by adding sprinklers to your building, you can drop the required fire resistance period by half, and that's pretty standard in the New Zealand code. I take issue with that personally, but I won't go into detail as to why I take issue with that at the moment. You can also see that the New Zealand code splits the requirements into protection of life and protection of property. And for some types of buildings, particularly commercial buildings and warehouse buildings, you have a much higher fire resistance requirement to protect property than you do to protect life. And that intuitively makes sense. Hopefully you would agree. But anyway, what you do is you go and you say, okay, how much fire resistance do I need for my building? It's an 18-story residential building. I need 60 minutes. How do I provide 60 minutes of fire resistance? You would then probably go to the concrete design code in your country. And in that concrete design code, it would probably tell you that columns and beams and slabs have to have certain overall dimensions in order to achieve a given level of fire resistance. And probably that you have to have a certain amount of concrete cover to your steel reinforcing in order to achieve that fire resistance, if it were a reinforced concrete building. If it were a timber building, maybe you would have to have some level of protection from encapsulation by plasterboard. And if it were a steel building, probably you would have to have some level of fire protection from spray applied fire protection or an encapsulation system using boards or something like that. But that would give you the fire resistance for your structure. But it's important to think, well, where does that fire resistance for my structure that is contained, for instance, within a building code for reinforced concrete, where do those minimum member dimensions and concrete covers to the rebar that give you a certain level of fire resistance come from? And the answer is they come from furnace testing. And furnace testing gives us what we call fire resistance, the 60 minutes fire resistance or 90 minutes of fire resistance, whatever you have from your table of required fire resistances. And the way that we've historically developed these fire resistances that we use is through furnace testing. And in a furnace test, what you do, if you've never done one, is you take essentially a very well insulated box that's the size of a room. So I've just conceptualized that here with a schematic. You take your structural element and you span your element. Let's say I was assessing a floor system, and you span your element across the top of that box. You put some load on your structural element that is intended to represent the service load that you would expect in your building. And you use large premixed propane or natural gas or oil flames to inject energy into the box to simulate a room fire. And then you wait for your structural element to become unstable, or you wait for it to fall down into the furnace. And when it becomes unstable or falls down into the furnace, we say that the time at which that occurs is the fire resistance period. And of course, in doing that, we have to use a standard temperature time curve to simulate the building fire so that all fire resistance tests are assessing elements against effectively the same standard. But it's really important to recognize where that standard fire resistance curve, the standard temperature time curve that we assess building elements against in order to derive their fire resistance, where that comes from. And if you look back throughout history, which is something that I've done, what you find is that comes from ad hoc tests that were done both in London and in the Eastern United States around the turn of the 20th century, so the late 1800s, early 1900s. And there were tests that were being done in an ad hoc way on flooring systems. And the researchers at the time who were doing these tests, they were trying to subject these flooring systems to the most severe possible heating that they were able to achieve in a box, a brick-lined box the size of a room. And in doing those tests, they measured temperature time curves, and those temperature time curves eventually turned into the standard temperature time curve. So you can see the standard temperature time curve that was developed first in the US and then also used in the UK, has later become the ISO 834 standard fire. I presume that in India, that there is a standard fire curve, which is, I would be very surprised to learn that it is based on something other than the BS 476 standard fire curve, which itself is based on the ASTM E119 curve that I'm showing here. So essentially all standard fire curves that are used around the world are based on tests from about 120 years ago that were never intended to provide any kind of normative assessment. They were intended to provide comparative assessment of flooring structures. And it's interesting that if I wanted to do a fire resistance test today in 2021, I would, in a much more sophisticated furnace than was used in 1902, but I would follow precisely the same temperature time curve that was derived from those tests in 1902. And what it's important to recognize for structural engineers about this is that the standard temperature time curve that we use when we assign fire resistance ratings to structural elements was originally conceived as a comparative test for alleged fireproof systems, that the standard fire is not a realistic representation of a building fire, most notably because it never runs out of fuel. Real fires do run out of fuel. The standard fire was set out before anyone had ever properly characterized fires in real buildings. And it was originally suggested without any intent to assign fire resistance ratings. So the concept of a fire resistance rating actually didn't appear until 10 years after the standard temperature time curve was proposed. And so then there's a question, if the standard fire curve doesn't look anything like a real fire curve, how do we relate what happens in a real fire in a building to a standard fire resistance period that is assigned on the basis of a temperature time curve? And the answer is based on some work that was done in the 1920s by a guy called Simon Ingberg. And what Ingberg did was he set a bunch of fires in a bunch of buildings, real fires with real fuel in real rooms with real windows, etc. And he measured the temperature time history within those real fires. And he found curves that looked like the red curve in this plot. And I've called that the natural fire curve. So a real fire in a real building. So the fire grows, it achieves some steady burning for a period of time. It then gradually runs out of fuel, and the temperatures in the compartment then drop. And you can see that in the curve. But the standard fire curve already exists. So Ingberg said, okay, well, what happens if I plot the standard fire curve against the real fire curve, the natural fire curve? How would I assign some equivalence between the two? How would I decide what duration of standard heating is representative of the severity of a fire in a real building? And he decided pretty arbitrarily that the way he would do this would be to compare the areas under the curves. So he said the area under the natural fire curve above some threshold temperature, which he took to be 300 degrees Celsius, again, arbitrarily, compare that area against the area underneath the standard temperature time curve above the same threshold temperature. And the point in time where those two areas are the same gives you the equivalent standard fire resistance time. So what Ingberg was essentially saying was that in real buildings, fires will grow and then burn out. And the fire resistance period that you would require for that building is equivalent on the basis that that real fire has essentially consumed all of its fuel and burned out. And that's a really important thing to recognize. It's also important to recognize that what that means is that the fire resistance times that are given in tables in building codes aren't real time. So 60 minutes of fire resistance doesn't mean 60 minutes of real time. It means an equivalent heating of 60 minutes such that the fuel load that you would expect in that building would be burned out and gone before the structure has failed in some way. And that's really important to recognize. So if that's the equivalence metric, then Ingberg had to say, well, how much resistance to fire do different types of structures need? And what he did was he then set a bunch of fires in a bunch of different buildings with different amounts of fuel in the rooms. And he measured the natural fires and he made his equivalence comparison to the standard fire. And what he found, I'm showing in this table here. So if he did a test in a compartment that had 10 pounds per square foot of fuel that could burn, the equivalence metric told him that he would need 1 hour of fire resistance. If he did the same thing with 60 pounds per square feet of fuel, much more fuel in the compartment, the fire burned for much longer, and he now needed 7.5 hours of fire resistance. So fundamentally, the amount of fire resistance that you require in a building is linked to the amount of fuel that you have in your building, which is going to be linked to the use and occupancy. So the more fuel you have, the longer fire resistance you require. And what that means is that fire resistance originally implied burnout without any intervention. So that's kind of the history of where fire resistance comes from. And I think it's really important that all structural engineers understand that, understand the simplifications that have gone into that. And in particular, if I just go back a couple of slides, understand that the schematization of fire resistance that we use, an isolated element sitting on top of a furnace with a maximum span of about 3 to 3.5 meters, is not at all representative of the performance of a structural element in a building where you have continuity in 3 dimensions, you have restraint, you have both sagging and hogging bending in elements, you have all sorts of interesting things going on in a real building that the fire resistance test cannot possibly characterize. And you also have all sorts of really interesting fire dynamics effects in a real building that the equivalence metric that Ingberg came up with in the 1920s can't possibly take account of. So fire resistance is an extremely approximate and extremely coarse way of dealing with fire resistance in structures. So route 1, to basically pick a fire resistance value from a table and then provide that, relying essentially on results that have come out of furnace tests, is an extremely coarse and approximate way of dealing with it. And the links between fire resistance and real structural response in fire, I would say, are tenuous at best. So those links are actually not very good. And there's been a lot of work done over the last 20 years to show that real structural response in fire is very, very different than the response to fire of elements when tested in furnace tests. and that furnace tests are not actually interrogating the things about structural elements that are most important, in particular, thermal expansion, thermal curvature, and the interactions between structural elements within three-dimensional structural frames. And none of those things are interrogated by furnace tests. So that's route one. Route one is following rules, and it's certainly not what performance-based engineering looks like. Route two in New Zealand is called the verification methods. And essentially here, what the New Zealand codes allow you to do is to not use the standard fire in making your assessment. So rather than using the standard fire, you use a more clever assessment of the fire that you might get in a building. And so basically they're saying, well, we know a lot more about the physics of fire dynamics than we did in the 1920s when Simon Ingberg was coming up with this stuff. And so we want you to use a physics-based idealization of compartment fire dynamics to figure out what the thermal loading of the structure is. So they say, you're going to, and if you do that, you're going to design your structure for what they call the full burnout design fire. So the natural fire that I showed in the previous curve. So how do you do that? Well, they give you three options in the New Zealand code for doing this. One, option A, is to use a time equivalent formula to come up with this equivalent fire severity, and they give you some rules to do that. So that is not very clever, and it's just a bunch of additional rule following. So I would actually classify that as a prescriptive approach. It's a prescriptive approach that doesn't require you to provide a fire resistance period against the standard fire. Option B is to use what's called a parametric temperature time curve. In particular, the structural Eurocodes that are used in Europe provide a means by which you can approximate the likely natural fire that you would get in a compartment for a given geometry, building materials, fuel load, and ventilation openings. You can approximate what fire dynamics you're likely to get. And you can use that as the design fire. So you follow rules to figure out what the fire is going to be, and then you have to impose that fire on your structure and assess the performance of your structure. Now, the problem in the New Zealand code is that how you assess the performance of your structure, how you decide that the structural response to the parametric fire is adequate, is not defined at all. So you're as a structural engineer, you're kind of left scratching your head and not knowing what to do. And then option C is similar, although now you're not using a parametric fire, you're using a much more sophisticated fire dynamics analysis that takes account of the actual fuel that's burning, the heat release rate that it's likely to generate, the growth rates, et cetera, et cetera. And that's quite tricky from a fire dynamics perspective. And then, of course, you have to take that fire dynamic understanding of the fire that you're going to get in your compartment, and you have to impose that on your structural system. And again, you have to assess the adequacy of your structural system to deal with that time temperature history, let's say. And so again, the code gives you no indication on how you would actually assess the performance of a structural response model in that scenario. So again, the structural engineer is left scratching their head. So the verification methods procedure in New Zealand, from my perspective, is actually pretty unsatisfactory. And I've spoken with a number of colleagues who practice in this area in New Zealand, and everybody agrees that it's actually not done very well at all, and is, effectively useless if you want to actually assess the structural response. So these types of analyses, it turns out, are not actually done, as far as I can tell. So route 2 basically helps you a little bit with the fire dynamics, but it doesn't help you at all with the structural engineering. How would you actually assess whether the structural response under a particular thermal scenario is adequate or not? Route 3, which is this, as I call it, this mysterious and wonderful beast, performance-based design, which may or may not actually exist in reality, is described in the New Zealand building codes as follows. The New Zealand building codes say that it is a performance-based code and it allows for innovation and uniqueness in design. And I agree with that statement. It says that departures from the acceptable solutions and verification methods can result in the best outcome for a building project. And I agree, performance-based engineering can absolutely result in the best outcome. If you don't have to follow the specific rules, you have much more freedom as a designer, much more freedom to innovate. And it also says that you don't actually, in the New Zealand context, have to justify why you're not following either the acceptable solutions or the verification methods. So any designer in New Zealand is free to take a fully performance-based approach if they want to. They then say, however, that the process of proposing an alternative solution or performance-based design, identifying the assessment methodology and the acceptance criteria, documenting the solution and navigating through the approvals process can be complex. I think that is quite an understatement. And they say that to assist with this, they've developed a document that they call the Fire Engineering Brief Process. And this is essentially a document that tells you how to interact with all the various stakeholders that might be interested, so as to make sure that everybody can agree what assessment methodology and acceptance criteria are going to be used in doing a performance-based design. And that's telling us something very interesting. So when you do a performance-based design, there are no rules. And so the only way to come to a solution is to work with all of the relevant stakeholders in order to come to some agreement about what represents adequacy with respect to the functional requirements of the building regulations. Well, that doesn't help me as a structural engineer. What I need to know is, what do I actually have to do as a designer? What are the steps that I need to take? What are the things that I need to show? And so in New Zealand, there was a recognition that structural engineers didn't have any guidance. And so they developed Practice Advisory Note 18, it's called, which is about the fire safety design specifically for tall buildings. And what it says is that structural systems in tall buildings need to be designed to remain stable for the complete duration of a fire, so for burnout conditions and cooling back to ambient temperature, and to maintain safe access and egress for firefighters and building occupants. So that's similar to the functional requirement that was given in the Building Act and the building regulations. And it then goes on and it says that useful guidance is provided by the Society of Fire Protection Engineers, the National Institutes of Standards and Technology in the US, and the Steel Construction Institute in the UK. Now, I've consulted the documents that are referenced in the New Zealand guidance, and none of those three documents help at all, frankly, with what would be considered useful assessment criteria in order to decide the adequacy of a particular building design. So if I take an example of a building in the United Kingdom that was performance-based designed for fire by the firm WSP, this is the Shard. It was the tallest building in Western Europe when it was designed and constructed. And the image in the center here shows the floor plate. So the main structural elements in the floor plate of a particular floor near the lower levels of this building. And the beams that are highlighted in red here are beams that have been provided with some fire protection insulation. The beams that are black have had all of their fire protection stripped off, and that saved the client some money. And in order to come up with this design, a finite element model of the floor plate of this building was developed and was exposed to a range of potential fire scenarios that might exist within this building. And they decided that they had demonstrated adequacy for this building. But what's interesting is if you read the report on the fire engineering strategy for this building, what you find is that some of those beams in that floor plate deflect more than a meter vertically in a fire. And something like 700 or 800 millimeters of that is irrecoverable after a fire. So the permanent deformation of the floor plate in the Shard after a severe building fire is on the order of half a meter or more. And one would have to ask the question, I think, whether or not that meets the requirement for loss of amenity in a fire. I would argue that floor plate deflections of half a meter over a 10 or 11 meter span in a high-rise office building near the base of the building represents significant loss of amenity and might make you ask questions about whether or not the entire building needed to be demolished after a fire. But of course, these decisions are decisions that need to be taken by the structural engineers, and they illustrate this point about what is it that would be considered adequate with respect to the performance of the Shard if you did actually have a fire. And if you think about that in the context of what the New Zealand building regulations require, you have to show that there's a low probability of losing equilibrium or the building becoming unstable. And that's fine. That's what was shown by the analysis that WSP did for the shard. But if you also had to show that there was a low probability of loss of amenity, I think you'd struggle to say that what was observed in those analyses was adequate. And these are the kinds of questions that structural engineers need to ask themselves when they embark on these types of designs. And so route 3 in the New Zealand context, the full alternative solution, the full performance-based design route, has a real problem because it actually doesn't provide any guidance on what might be considered adequate with respect to meeting the requirements of the functional building regulations. It doesn't tell you what probability is low enough that it would be considered adequate. And so at the end of the day, what these codes, these performance-based codes in New Zealand, or indeed all performance-based codes that exist around the world, what they're saying is, I think best summarized in a paper that was written by this chap here, whose name is Ruben van Coyle, who I've worked with for a number of years. I'm a co-author on this paper, but Ruben van Coyle is the brains behind the operation. A few years ago, only 2 years ago actually, we published a paper which is called The Need for Hierarchies of Acceptance Criteria for Probabilistic Risk Assessments in Fire Engineering. And what we basically were asking ourselves the question, how do we decide what is adequate when we're doing a performance-based design for fire? And the conclusion that we came to was that the only way we could define adequacy was, as I've written here, that adequacy can be defined by saying that an objective, diligent, and competent fire safety professional would consider the spectrum of possible consequences and their associated probabilities associated with any given design to be acceptable to normal societal stakeholders. And that's actually a pretty big statement with a lot of subjectivity in it. And it demands an extremely high level of competence and professionalism from the fire safety engineers. And so at the end of the day, performance-based design codes are saying, with respect to adequacy, if you ask a performance-based design code, what do you mean by adequately? What do you mean by a sufficiently low probability? The answer is, what they're all saying is, we don't know. The codes don't know. The codes believe that you, and by you, we mean all of the stakeholders, have to get together as a group and you have to decide together what is adequate. And in doing so, we have to, as a society, we have to hope that all of the people involved in that process are objective, that they are diligent, they're professional, and they're competent. And so if you want to consider moving down a performance-based route, my view is that you have to make absolutely certain that within the process of permitting performance-based design, that those people who are charged with designing or assessing or approving performance-based designs are objective, diligent, and competent. And you have to have mechanisms in place that require those things to exist, because if you don't, I don't think those things will exist. So going back to one of the slides I had at the beginning, as I've said, I very strongly support the idea of functional building regulations or performance-based design. But if you're going to do it, you must insist on competence, and you must have mechanisms in place that require that competence to exist within the processes. So hopefully that's given you some of my thoughts about this particular topic, and I look forward to some discussion now with anyone who's on the call. Thank you.
Thank you. Thank you, Professor Luke.
Thank you, Professor Luke Bisbee, for the wonderful presentation. We will take the question answer at the end of the panel discussion. Before we move to the question answer, we will have a panel discussion. We will take view of our eminent panelists. Our eminent panelists today with us are Dr. Gaurav Srivastava, Associate Professor, IIT Gandhinagar; Dr. Gopal Chandra Mishra, former Director, Delhi Fire Service; and Mr. Nitin Gupta, Director, AirCorp Associates. Professor Gaurav Srivastava, his professional and research interests involve assessment and design of structural and non-structural building components subjected to fire. He has worked towards analysis and design of reinforced concrete and steel structural systems subjected to the fire, and assessment of building package systems, their components under fire, and development of new cementitious materials with specific performance requirements. And beside him, we have Dr. Gopal Chandra Mishra, who is a former director of Delhi Fire Services. Dr. Mishra is in fire engineering science and technology, having 37 years of experience in the profession in various capacities. He started his career from Indian Petrochemicals, Vadodara, served in National Fire Service College, Nagpur, and Delhi Fire Service. He retired as director in March 2019. He is the immediate past president of Institution of Fire Engineers. He is decorated and President Fire Service Medal, decorated with President's Fire Service Medal for Distinguished Service and President's Fire Service Medal for Meritorious Service. He is first fire engineer to receive Eminent Engineers Award 2018 conferred by the Institution of Engineers. We welcome you, Mr. Mishra. Then we have with us Mr. Nitin Gupta. Mr. Nitin Gupta graduated from School of Planning and Architecture, Delhi in 1992. In his journey of the last 24 years in the profession, he has played various roles in the planning, design, and construction of multiple projects, interior design, buildings, and campuses towards township and design. First, I will ask our structural expert, Professor Gaurav. I would like to take his views on what is happening in India, and I would like him to throw some light on our current codal practices. Our codes permit performance-based design in IS 1642 to some extent. It says test-based designs can be done, but it is not being widely used. So I would like to know what extent these are being used in our country and what are the limitations we have. And then also, are we referring to Euro codes and other codes as Professor Bisbee is mentioning? And are our consultants competent enough to handle these things? What is the status in our country? I would like you to elaborate on those. And will it help if we have elaborate codes with us? Will it improve our capabilities? Mr. Gupta, please. Professor Srivastava, please. To Gaurav.
I thought, sure. So thank you. I think it's a very interesting question, and the backdrop is also set very, I would say, ambiguously.
Yes.
As the performance-based design is quite ambiguous. And I think that's the beauty of it as well. So we all fear the unknown, but most of the beautiful things also come from the unknown. So as far as the state of structural engineering, in my perception, is concerned here in India, most of the times what we do is we design for the usual. When I say usual, fire is not one of them. We design for the usual loads, dead load, live load, wind load, earthquake loads, in certain cases, snow loads and other impact loads. Right? So that is what is the basis of all design that I've seen. And sometimes the structural consultants check or pay attention to the fire rating if they at all do that. Most of the times the structural fire aspect I have seen not being considered in the mainstream design. The aspects of fire which I have seen being included are mostly related to firefighting rather than the structural response of the system. So from that aspect, I find that there certainly is a big gap, even in considering prescriptive structural fire design. So I think we, as you were mentioning, we have this IS 1642, which mentions for what occupancy, what kind of fire rating is to be considered for design. The earlier National Building Code also gave a table which had for each occupancy what kind of fire loads to consider for design, what are the design scenarios. That was perhaps tending towards the Euro codes, but not quite there. And then also, there is this IS 3809, which describes the kind of furnace to be used for assessment of the fire ratings. The time temperature curve is exactly the same as ISO 834. And I think very recently BIS, our course, they have actually adopted the ISO 834 and other related standards above the IS 3809. Okay. So that kind of testing is there, but I think what Professor Luke was also mentioning, all of these are still prescriptive designs. They are still not getting up to the true performance-based designs that we really talk about. And I feel we are not even there. So although our codes are there, our codes have the provision of doing a better prescriptive design. We are not even doing that. So to reach to the next level, which is true performance based, that I'd say still some more effort and time until we get there. And as far as Euro codes are concerned, when I teach a course here on structural fire design, so for that I do consult and I teach that code as well because of the limited support available from the Indian codes. So we do go over some of these calculation methods, but still they are, even Euro codes, they are, I mean, in general, they are still, I would say, prescriptive. So you can define a design scenario, you can, define what design load to take, design fire load to take, and you can derive an equivalent fire rating based on the different fire scenarios. But that is still not fully performance-based in that sense. So yeah, I think I would stop here in case there are any questions.
Okay, so you mean even if you follow Euro code, it is not complete. It is not a complete guidance to the structural consultant, as Professor Bisi was saying. Structural consultants, they're not clear what to do and all that. So if we have to have codes, it should be more specific kind of, even if you have to use the scenarios, real scenario or something.
So let me I think give you an example of this COVID-19 which is going on, right? So if there is a known ailment, the line of treatment is known. So there is more certainty and everyone is more confident. Right? And
Yes.
competence is not supreme. I mean, for normal fever, you can go to any doctor, they will give you a prescription drug and you can get cured. But when COVID came, it is a totally new kind of virus. No one knows how does it behave. So this is where the true performance-based thinking comes. That someone who is competent enough to understand the risks and the associated other factors will have to really look at all of that, right? So performance-based design in a way is like that.
Yeah, that is a good point you have made. That if we have to move towards performance-based, we have to give a clear line of action to the consultant how he has to process. I mean, it may not be 100% performance-based, but at least if it is specific, then acceptance criteria can also be made accordingly. So it will be partly supported with some prescription, and it will be performance-based to the extent that we have our own fire scenarios or something like that. And then we do some calculation check, and then we can do some sample testing. So I think if you're right, based like we did in COVID, if we have a clear line of action, then the things may improve. And my next question will be to our fire engineer expert, Dr. J.C. Mishra. Now, in performance design, instead of standard fire, the actual expected fire curves are to be used, preferably, or we can say it can also be used, or it is to be validated with that, because we are talking of fire loads, burnout, and then accordingly we should have based on the fire load, we should have some curve which we should be able to draw, as some examples were given by Professor Bisi. So my question is, do we have some data in our country to generate this kind of curves? With our fires, are we generating some data also when we have fires in our country, that with this kind of load, how much duration of fire was there and what temperatures it had gone to? And my second question is, even if we permit, if we go for performance-based design, will we permit it or specify it, or we simply again stick to the standard fire and say the fire rating as we are doing it now? So what are your views on these aspects, Professor Mishra?
Sir, thank you very much. Now two issues you have raised. One is that are we collecting the data? Let me be very honest on this issue, that this country does not have any practice or any obligation to collect the data, analyze them, and then draw out the inferences, and then tell other stakeholders that they carry on with their works. The second point that you have raised is about the fire conditions and the fire loading and the fire resistance rating. Now, Professor Gaurav has also mentioned, and Luke was very focused on this issue, that we do not first thing say when you want to have something which is adequate, now you should also have at the same time the criteria for which the buildings or the structure is to be designed. Now, from the structural engineers have competence, their competence is determined based on how elaborate the codes are, and that will be decided based on as to what is the data available to you. Now we lack at both the places. We do not have data known or collected and analyzed. And second, that we have no standard fire in the country. And when you design the system, the loading is also not fixed here. Now, when you design the building, you do a very generalistic, or you take a very generalistic approach and design the building. Now, any fire, if it is falling within the, say, below the ISO curves that we have followed, you are lucky that it will survive the burnout. But moment the conditions are a bit different, then it is not going to fall on the ISO curves or within. It will be crossing the limits. And we have seen many collapses during the firefighting. Now, structure, the columns and beams may survive. In many cases, they have survived. But the floors have caved in. Now, there is some problem somewhere which the structural engineer has to look. And second aspect is how much water do we use during the firefighting. Now, if we see that fire is big, we go to 6 or 7 jets at a time. One jet is 600 liters a minute. So 7 jets means 40 structures which have survived the temperature conditions have failed because of the excessive loading that we have done when the structure was weak. So it is not known to the fire service community as to what this structure is designed for, and we have no confidence. Say, I'm saying it with full responsibility that the fire service community does not know, or they lack confidence in the design of the building. They do not know whether this structure is going to survive for the duration, dependent on the fire load. Now, fire load is increasing. Now, say, like other countries, now the Professor Luke was mentioning about the data that we have. And initially, when you design the building, it is a general antibiotic dose, say, which fits for all the say situations. Now, what is our problem? We are neither prescriptive nor we are performance based. It is very selective approach and also not based on the facts which are necessary to be considered for the design of the buildings from fire and life safety point of view. So this is the total scenario.
Okay. Yeah, this is there. One more question I have to you is that are our fire scenarios similar to the ones in developed countries, or they are much different? I mean, if they are similar, we can adopt their data. And if they are totally different, then even that data is not useful to us. Those curves which Persuasive was showing in the natural fire curves and etc., that won't be useful to us. So what is your take on that?
This is the crux of the whole problem that we are facing. Now, we have been saying most of the standards that we have today in the country, or the provisions in the National Building Code of India, all have been copied from the countries which have different culture altogether for the occupancy of the buildings. Our kind of loading, the mixing, we today precisely, we do not know. You go to market, buy a building material, you do not know what it is rated for. So in a building, you have mix of these materials which have unknown ratings. And now they are placed at a place where a rating is required.
Okay.
So taking the curves from the developed nations would not help us. We have to see what we have, the manufacturing of the building materials that we have in this country. They should be tested first and certified for certain applications, which is not happening in this country. Other developed world, if you look at, if they say fire door is rated for 2 hours, means it is rated for 2 hours. But if you buy a fire door in India, it will vary from place to place. That rating does not remain constant for reasons unknown. So copying the developed world would be another step back.
Okay.
So what we have to do, we have to develop our own system of testing. This fire science and fire engineering is lacking very badly on these issues. We do not have any academic institutions which has worked or working on these aspects to give the public a final certificate. Look, that this is the material you selected for the fall ceiling. This is what the, say you want class 1 rating, then these are the materials and for the class 1 flame spirit. So you have a structure, and then when you do the loading, you do not know what you are loading it for and what it was designed for. So there is a gap between the occupied building and the design building. So that gap has to be minimized. Then only fire and life safety solutions, whether by prescriptive code or by the performance-based code, will succeed, in my personal opinion.
Okay. Thank you, Dr. Mishra. So what I understand from your talk is 2 points you have raised. One is we need more research in-house to generate data on the fire loads, on the type of materials, vulnerability, and those kind of issues. And second is that we should not have a simply performance-based approach. We have to have a mixed approach initially, prescriptive and performance-based to start with, so that we cannot jump to performance-based, because the European data or the developed countries' data will not be truly representative of our fire loads. So we have to have some minimum prescriptive guidelines, even if we are going for the performance-based design. Thank you,
precisely.
I move to Mr. Nitin Gupta. On the use of materials, Mr. Gupta, are we moving towards the use of less combustible materials? This was a point raised by Dr. Mishra also, that what materials we are using, we should know that, and why we are using more combustible materials. Our codes specify use of less combustible materials in buildings above 15-meter height. Now, is it being followed that we are using less combustible material of 15-meter height? And is it being checked by somebody? And comparing to construction practices in other developed countries, do we use more combustible materials or less combustible materials in general in our multi-story buildings? This is what I would like you to comment on, and any other comment you want to make on this.
Sure. First of all, good evening, everyone. And thanks a lot, Professor Liu, for the wonderful talk. I think we are all more learned now. And Mr. Arora, to specifically answer your question, when it comes to high-rise buildings that I am doing, or most of my architecture fraternity, I think we are very conscious to avoid combustible materials. So I think that I would say, I would give credit to my peers also, that generally when it comes to complicated buildings like hospitals or hospitality and high-rise buildings, we are making a very conscious attempt to avoid using combustible materials to the least, I would say. In some situations one has to use wood for the doors, or for certain furniture elements. And similarly for in case of certain high-end projects, I would say one has to use soft furnishings. So that is where, but that is it. I think beyond that, the use of combustible material is really limited. But yes, I think in the residential buildings where the individual tenant comes with his own furniture, there one has kind of minimum control on that. So other than that, just to share with you my own views, I think the topic was absolutely brand new to me. I had never heard of something like this, or even imagined that something like this is even happening around the world. I would say within my office, it is almost every day that we are applying or discussing a fire approval for one building or the other in, one part of the country. So it is genuinely a struggle, because each time our designs are changing, planning is changing. So even to get the prescriptive, method approved by the fire department, believe me, it's a struggle for us. It is it's huge amount of discussions and deliberations that have to go in. So that being said, I think it's a far outcry to imagine that for generally all the projects, one could go in for a performance-based, design system. Just to give you a very small example, it is right now we are getting approvals, a small portion of the AIMS Jharkhand that has got completed. So, the director's villa, it's a 2-story bungalow, and the local fire department has asked us to put a sprinkler system there. That has been given to us in writing. So that is the state of affairs, and nobody can do anything about it. Even though we cite NBC, they said, state government, state department has the right to go over and above NBC. So in that scenario, I would say to go for a performance-based is again a big demand. But at the same time, there are projects that we are doing. Pragati Maidan redevelopment we are doing in Delhi. And then the India International Convention Center in Dwarka. Both of these projects, have such complexities. They have covered very large exhibition halls. So obviously, even the existing National Building Code could not, suffice in terms of the requirements. If you have an exhibition hall which is 160 meters by 160 meters in the dimension, how do you make sure that you have fire exit staircases? If you start giving exit staircases in middle, then the continuity and the space of the exhibition hall gets broken down. So in those scenarios, I saw automatically, and credit to, I think Dr. Mishra was also involved with us, in advising us as to what we need to do. So there automatically, the performance-based design, now I'm figuring, kind of came in. It was, I would say we were trying to say that, we are innovating, but in a way we were doing a performance-based design, analyzing how the function is going to happen. But yes, again, coming back to your question, it is, we do deter, using any sort of combustible, materials as least as possible.
Okay. Now you said high-rise buildings. Now our code says any building 15 meters above. Are you saying that all 15 meters above buildings, this precaution is being taken by everybody?
Well,
somebody is checking on this or not?
I would say that I would go a step further. I would say that complicated projects like hospitals, for example, healthcare.
No, I am not saying a complicated project. I'm asking our code says normal any building above 15 meter height. This should materials. So is this provision being adhered to by all architects or by government? Is there any checking on that?
Generally, yes. Generally, yes.
Okay.
So even when I say high rise, I'm classifying above 15 meters only. And I'm saying for complicated buildings, even less than 15 meters, we are following this as as an advice.
Yes. Thank you, Nitin Gupta. You have enlightened us on that. It is at least in that part we are doing some advancement and use of less combustible materials. Of course, more data will be generated on that. It will be more helpful. Now I will again come back to Professor Bisbee. There are a few questions from the participants. You can see the question answer on your screen. There are 3 questions. If you can read and answer yourself, it can, or I can read and then you can answer as you wish.
Sure, yeah, no, and I mean, as the discussion's been going on, I've been trying to answer a few of those. So you can see there are 6 answered questions where I've tried to answer briefly just by typing. I mean, the first two questions, unfortunately, would require, I think, hour-long seminars,
Yeah,
each,
yeah.
if not a full semester, if not a full semester length course. So I'm not sure I can answer those first two questions concisely, if I'm being honest. But I mean, certainly, I could. If Sushil Dhawan, I don't know if my email's been made available, but I'm happy for colleagues to share my email with people who participated today. And if anyone wants to email me and ask for maybe one or two references for key things to read that I would suggest, I'm happy to propose things. This area of performance-based design for structural fire safety is not new. It's been going on for 30 years or so. But still, there are not many very good textbooks that articulate, I think, the issues up to date very well. The third question, I'll just read it. In my stint in Dubai for more than 15 years, dealing with tall buildings ranging up to 350 meters, I would say the fire code there has evolved over a period. I agree. The good part of it was things were forced and adopted by the designers, contractors, and developers. I wonder how much of such control can be imposed in a country, I presume that is as big and widespread as India. And I think those comments came through in what Mr. Gupta was saying a few minutes ago about some of the issues around demands by approving authorities, and whoever's managing the building control process. One of the reasons, like I said at the beginning of my talk, that one of the reasons I moved to the UK was because the UK was a jurisdiction at the time in 2008 where performance-based design was permitted by the authorities having jurisdiction. So those people who were charged with approving designs, there was two things about them that were really important. One was that they were open-minded and they were willing to have a discussion with designers. And the other is that they were unusually competent. So the building control authorities that were operating, particularly in London at that time, many of the local building control officers and the London Fire Brigade themselves had an in-house fire engineering team who had been trained up, had been seconded to some of the top firms in consultancy who were working in these areas for periods of 6 months. And so there had been a lot of learning going on in London for the 5 to 10 years prior to that, which meant the approving authorities, so you had a regulatory structure through the legislation that explicitly permitted performance-based design. You had a consulting industry where you had people who had been educated sufficiently that they could be proposing performance-based designs based on physics and science and understanding. But most critically, I think, you had approvals authorities who were open-minded and competent. And until you have approving authorities who are open-minded and competent, there's no point even trying to go down a performance-based route. Because in the UK, we talk about what we call an approvals risk that is associated with performance-based design. So whenever you're dealing with a client as a consultant and you say, I think for your particular building, maybe we want to take a performance-based approach, there's a really important conversation that you need to have with your client early on, which is, just so you know, this does represent a risk to you as the client that whatever we propose might not get approved, and that we might have to go back and change the design and make modifications, and that costs time, and time costs money. And so there's a risk associated with taking a performance-based route, which we call the approvals risk. That approvals risk, I think, is much less, for instance, in London, England, where you have these very competent building approvals agencies, than it would be, frankly, in Scotland, where I work. If you tried to propose something in Edinburgh or Glasgow in Scotland, that would be approved maybe and wouldn't generate an approvals risk in London, in England. It may well generate an approvals risk in Scotland, because the approvers in Scotland who don't see the same numbers of buildings of the same size as we would see in London, they don't have the competence and the open-mindedness necessarily. That's not a criticism of them. There's not been any requirement for them to have that open-mindedness or competence historically. So you end up in a bit of a, I don't know if the expression works in the Indian context well, but a chicken versus the egg situation. Which comes first? Performance-based design, which then requires approvers to be open-minded and competent, or do you need open-minded and competent approvers to be brought into existence first before you can propose performance-based designs? And that's something that I don't think will happen spontaneously. So probably someone in India needs to if this is what you want to do, someone in India needs to forcefully take action to try to make sure that these types of things can happen. But I have no idea if that's realistic. You have an absolute, from a population perspective, you have a country that is larger than anything I can possibly conceive of. And I'm sure that introduces all sorts of very interesting challenges around regulation and jurisdiction that I can't get my head around, I'm sure.
You're on mute, Mr. Arora. Kindly unmute yourself, Arora Sahab.
Sorry. Thank you, Professor Bisbee. Now I will request Mr. Manoj Mittal to propose a formal vote of thanks. And now I think there is no other question.
I think there is some question by Abhijit Kulkarni also. Has it been answered? Yeah. I will read that question.
No, he has tried to answer this question basically. This is what you're asking.
That's what I just tried to answer that one.
He tried to answer that. To the extent possible.
Earlier I saw one question from Vipul Ahuja also, but I am not seeing now.
No, that is not there.
Answered. That is answered.
That is answered.
If any more question is there, anybody can ask. Any panelist, if you want to ask anything, can ask. Professor Bisbee is here.
Okay. Right.
Any other comment from any panelist is also welcome.
Yeah.
We have few minutes left.
We have few minutes if anybody has any other question.
Okay, if I may say something.
Sure, please.
So, I was just listening to the comment by Professor Gaurav Srivastav in the beginning. He mentioned that, in fact, there is a gap between what is there in our codes and National Building Code and what we practice. So, first of all, we are on the one hand talking about a performance-based design, which Professor Luke very clearly mentioned in his opening few slides, that the prerequisite for having a performance-based design is competence and functionality. And here we have a situation where you are saying that the compliance to code itself is a challenge. So therefore, I would like Professor Gaurav to say something about this, because what is it that we need to do, first of all, to close this gap between the compliance and the code? And then we go to the next step of improving our code.
In my personal view, I think we can take instead of an 80-20 and 90-10 approach, where let's say 90% of the projects are of routine type, where that kind of things have been done earlier. So we can adopt the good practices, we can continue to follow the prescriptive approaches, and we can reinforce that, right? So even prescriptive approaches require competence to a certain extent. So what Mr. Gupta is mentioning about getting approvals, in those discussions essentially hover around different people at different levels of competence. So someone and also open-mindedness. So someone may be totally close-minded to the fact that if something is mentioned in the code, it is a gold standard, it cannot be violated. But if we are to go the performance-based route, we need to be able to question that, right, with an open mind. Whether it is fine that it is there in the code, but all the basis of performance-based design, in my view, is we should be able to question that. We should be able to propose better solutions than what is there. And the remaining 10% of the projects, I feel we should really aspire. We should really aspire to break the norms, and that too is not easy, because it comes at a cost, not just competence. It will require more time. It will require perhaps more funds. And many times we are mostly in a hurry to consume the funds which are allotted for a particular project. So that mindset also we need to let go a little bit.
Okay, thank you.
Now, can instead of saying 10%, can we go it like that? If the building is required to be 1 hour rating, then we go only by the prescription. And if we have to go for higher fire ratings, we can have a more detailed approach, elaborate approach on that. Will that approach be
The decision
practical?
But who will take the decision? This building will be 1 hour rating and.
No, but that ratings we have to specify based on the occupancy and zone. Then we have to specify what kind of fire ratings.
That will be specified in the code. Then it's okay.
And then after that, then we can allow that for this thing, you can have a detailed calculations.
Actually, the decision
To start with, I mean, it's mixed approach only. It is not totally performance based kind of. It is a mixed approach we have to follow. Like Dr. Mishra was saying, we cannot simply go to directly performance based. We don't have data on that also.
Actually, I feel that the initiative at the moment really lies with the approving authority. If they were to start promoting performance-based design, I think that would really kickstart. Otherwise, at this moment, I think, as Professor Lube also said, it'll be a huge risk for the client and the consultant to go through the whole design process. And then when they approach, if there is open-mindedness is not there, it would really set everyone back.
Mm-hmm. That is why we are, as Professor Gaurav had said, that it has to be a kind of line of action has to be clear. I mean, how it has to go and for what cases, what is to be done. So that the approving authority will also have some line of action, how they have to approve it. That's kind of thinking we should have.
Right.
We need to discuss more and then come out with something on this.
True.
So if there are no more questions, then
I just want to comment.
Please.
Now, after listening, everybody, the basic issue now, see the design by an architect, say by an architect, or by a structural engineer, or by the plumbing engineer. All these designs are prepared by the experts. And now when you go to the fire authority for approval, they are not equally competent. So now to understand and approve your design or the design by an expert, they should have equal level of competence or even one step ahead of that, which is not there. So now whether performance based or prescriptive, now the third dimension that I am adding to this discussion is, why should not India take a lead to give a self-regulatory regime, which I have in Delhi, I have done for many occupancies, that it is a self-regulatory regime. The fire department is not competent to examine your designs. So now I leave it to you, you design, you certify that it is in conformity with the codes and standards and also in accordance with the law of the land. And you give a certificate, take the approval, or it will be a deemed approval. This is what I have pleaded. Now, no structural engineer, no architect with saying with the sincerity, and over the years I have learned it, that nobody is prepared to certify that this building is in conformity with the law of the land. And impliedly the standards and the good practices that are referred to in that code. So if the fire department approval, now say whatever you say decide to achieve, you can achieve that. And here in India, the fire and life safety issue is not important. Important is to obtain the approval, so-called NOC. So now this is the mindset that I do not know what is the fire load in the building. I have designed this building and you sign as a fire authority that it is in conformity with the code. So if you want to have a very honest view honest view to fire and life safety, then in that case, what you'll have to do, you should know what this building is designed for. Now, Mr. Gupta has mentioned in Pragati Maidan, we were suffering, we were finding it very difficult to find out as to what is the fire load that this exhibition hall has been designed for. Now, sometimes during the exhibition, you may have the aeroplane also. Sometimes you will be displaying the helicopters, and sometimes you will have a fate from the Assam. So now full of combustible materials. So now we have no regulatory regime, or there's no self-imposed discipline on loading of the building. It changes immediately. Say now the best example. The hospitals that have been designed for 500 beds have been overnight changed into 750 beds within the same space. Now, where is the fire and life safety? Now, during the dengue and other such diseases, when we have those epidemics in Delhi, now you have corridors filled with the patients, all chairs and say patients are sitting, or the stretchers are there. All escape routes are blocked. Now, stability is not the only issue. Now, most of the people die because of the asphyxia. Now, if I talk of stability of the structure under fire conditions, that will be half the truth. Now, I must consider the integrity aspect, and I must also consider the insulation aspect. Now, hospitals, see that they are using the polyurethane foam mattresses, all plastic materials. Now, it is not only the structure which has to say, which contributes for the fire and life safety. Most important role is played by the loading of the structure, the nature of combustible that we use, the toxicity and the poisonous components of the combustion that we have during combustion. Now, mix of the plastics. See what level of what grades of plastics are being mixed in our loading of these structures. So you have designed it for a load, but that load is not giving you the true picture that we have seen during the actual fire scenarios. So tenability, we have not decided as yet how much my structure should say allow the occupants to stay in the building, whether for 15 minutes, 20 minutes, or 1 hour or 2 hours. So all is not focused and should not remain focused, in my personal opinion, on the stability of the structure, if the life safety component is added to that. So it must go beyond the stability of the structures, and that would perhaps reach the level of protection that we want. And that will be the satisfying level for the fire and life safety in buildings. And also, last point which I want to make is that it is not the high-rise buildings alone. We are more focused on the high-rise buildings. But Delhi statistics, 90% of the Delhi deaths are taking place in low-rise residential buildings.
Okay.
So we should not only talk about the high-rise buildings and say they are something different. Fire taking place at a 15-meter level or 24-meter level is behaving the same way as it behaves in a ground plus 2 structure. So why should there be a different dose? When I talk of performance-based, then my fire conditions are the same. So they should have the right dose for fire and life safety protection. Thank you all very much for giving me this opportunity to speak and share my views. Thank you very much.
Thank you.
Thank you.
Okay.
Any more comment from any of the panelists?
I think everybody has spoken now.
Okay. Mr. Manoj Mitra.
Okay. Really, it was, yeah, it was really very wonderful and very focused discussion and presentation. Although it was quite a new topic for our listeners on structural fire safety. And actually, it all started with the Institution of Fire Engineers when they sent a mail to us that we need to do something on that. And then we had a MOU with the School of Planning Architecture. I discussed with Dr. V.K. Paul. I think he's not there today. And then we have this MOU, and under this MOU, we decided that we will have a series of webinars and other technical events focused into the area of structural fire safety. And we will also try to publish some kind of a guideline of standards for the benefit of professionals. So from that point of view, this was the first webinar. And I must say, it was a very, Professor Luke gave a very good understanding of performance-based structural fire safety. Now, I think everybody is clear what is that, and it's a basic framework is clear to us. And then all panelists, Professor Gaurav Srivastava told us about the Indian scenario, IS code positions, and all those things. Or Dr. Mishra actually told the truth, actually, what is happening and what is to be done. And similarly, Nitin also told various aspects. So now we know basically what is this performance-based structural fire safety, and we also know a lot of issues are there which we need to address in future. So now in future we will be planning and we will be undertaking more webinars focusing into different areas of structural fire safety. They may be planning and designing aspect. They may be from a structural point of view. They may be a material point of view. They may be the BIS codal requirement point of view, or maybe from regulatory point of view, or from compliance point of view. So there are several issues, and we need to address each of them in detail. And only then, and also our aim is to create a resource pool of knowledgeable persons who can really contribute in this direction. And I believe that through these webinars, we will definitely get some such interested people who can work in this direction, and we will be able to really create a good document, and we will be able to create a good awareness about this important aspect, which is generally missing and being neglected by, I think, everyone, not only structural engineers, planners, fire safety officers, and also by the researchers also, and even users are also not aware what is their right and what they should look for. Even the buildings are designed, constructed, thereafter those provisions are not being maintained. Sprinklers are not working, staircases are blocked. So what is the point of having design and construction if they are not being maintained? Ultimately, they will not serve any purpose. So we need to address all these issues, and I believe in time to come, ISTRUCTIVE, with the help of School of Planning Architecture and Institution of Fire Engineers, we will and also associating with our other people, we will be doing that. It was a really wonderful experience, and I thank Professor Luke joining from UK. It was a really very learning experience for us. It was very nice presentation, very effectively made, and all the panelists. I thank everyone for this presentation. Thank you all the participants also.
Thank you, Professor Luke. Sincere thanks for accepting my invitation and enlightening us. Thank you.
You're very welcome.
And
thank you for the invitation.
all the panelists and the moderator for making it a very lively program.
Thank you.
One thing I want to tell,
webinar.
in December first week, there is an international conference in India. Would you like to invite Dr. Luke to present a paper in that conference?
Yeah, sure. We can extend our invitation to Professor Luke.
Yeah, it's a new chapter, and this is needed for India. So if COVID permits, we will invite him. If COVID permits, it is up to him to visit the India also. It is one of the biggest conference and exhibition in India. Okay, sir. Thank you. I'm having some urgent call, so I will leaving this meeting.
So we all are leaving.
Okay. Thank you, sir.
Thank you. Goodbye.
Thank you. Bye-bye.
Thank you.